Thanks. I'll begin with a word of prayer. So, Dearly Father, we thank you for this morning. Again, Lord, I thank you for these students. I just pray that you just bless this class. Help us again, Lord, to glorify you in what we do this morning, Lord. In your name I pray. Amen. So let me just briefly review what we did last time a little bit. So I introduced the inverse sine, and inverse, well, I didn't introduce inverse cosine, but we could introduce inverse cosine, and inverse tangent. Now, so they're actually technically local inverses for sine, cosine, and tangent because they're not the inverse for the whole domain, right? They're just the inverse for the sine or the cosine restricted to a particular subset. So, like for example, inverse sine we talked about we're going to use from minus pi over 2 to pi over 2 as the domain in which we're finding the inverse. So that means that this second identity is for minus pi over 2 less than or equal to x less than or equal to pi over 2. How about the first one? Where's the first x coming from? I can only take the sine inverse of something in the range, right? Right. Now, I wrote that with y last time, I think, but you could also write it with x. But you have to understand those are different x's, right? Now, let's see here. This one, again, since x is in the range, since the inverse function's taking it, right? So this is for minus 1 less than or equal to x less than or equal to 1, and for 0 less than or equal to x less than or equal to pi for the cosine. Right, so inverse cosine is the inverse for cosine restricted to 0 to pi. And then, now, so sorry, let me try to rescue this. Don't do this. Inverse tangent, well, what is the range of what's the range of tangent? On any, between any two of its asymptotes, it covers all real numbers, right? So this is just for any x, right? For x in the reals. And, sorry about that. And this second one is just for what? This is for minus pi over 2, not included, less than x, less than pi over 2. Right, tangent has trouble at pi over 2, right? It's got division by 0. So those are your basic inverse trig functions, right? We talked about how to calculate what did we show last time? We showed that the derivative with respect to x of inverse sine of x, 1 over the square root, 1 minus x squared, and then at the end of class, I argue that the derivative with respect to x of inverse tangent of x is equal to 1 over 1 plus x squared, right? What other inverse functions would we like to, deal with? How about, what's the derivative of inverse cosine? What's the derivative of, what else? How about these guys? Like inverse secant? What about the derivative of like inverse cosecant? Right? Are there any other? How about inverse cotangent? We might also be interested in that, right? Now, we could calculate the derivative of inverse cosine the same way we did it last time, all right? So I'm going to just do that just as a warm-up here. So let y equal inverse cosine of x, right? And that's for what? For x where x somewhere in minus 1 to 1. So right now I'm trying to calculate the derivative of the inverse cosine, right? So I'm worrying about this question mark right here at the moment. So what's our next step? If we let y equal inverse cosine, following what we did last class, we take cosine of both sides. What's that give us? Cosine y equals to x, right? Differentiate implicitly. What does that give us? That gives us minus sine of y times dy dx is equal to 1, right? And then so we can solve for dy dx, which is after all what we're after. Now what does sine look like? Sine of y look like if we're between minus 1 and 1? Last time we were able to say, oh, cosine of y is positive between minus 1 and 1 because we're on like this part of the cosine, right? But you see, we don't have such a luxury now. If you look at sine between minus 1 and 1, it takes negative values for negative values, and it takes positive values for positive values, right? So as I think about, I'm going to have to break this into cases, right? So what I'm thinking about here, of course, is I want to get back to cosine because that's what x is. I want a formula in terms of x, right? So let me see here. Here's the logic. This should be less than 0 or greater than 0. What should this be on the basis of just basic calculus 1 and the graph? Like cosine is what? Decreasing, right? So the derivative has to be negative. So that's not up for grabs. This has to be less than 0, right? And I expect it'll be undefined where? At the endpoints, you know? So if, no, let's see here. How about cosine squared y plus sine squared y is equal to 1, right? So I can solve for sine, which tells me what? Sine of y is equal to plus or minus the square root of 1 minus cosine squared y. Yes, sir?
Wouldn't it be greater than 0 because the negative in the denominator gets up?
Oh, thank you. Yes. Oh, no. No. You fished me in there for a second. But the point is not that I know that this negative is not coming from this. It's coming from the sine. This is the rate of change of inverse cosine, which I know is negative.
Yeah.
However, the sine quantity, it's either positive or negative. So, like, just follow me here for a second. You'll see the point.
Okay.
So sine of y is either plus or minus the square root, right? So the square root of something is positive, right? So in particular, if 0 is less than or equal to y is less than or equal to 1, then sine of y is equal to the square root of 1 minus. Let me just go ahead and, what is cosine squared y? I'm getting tired of writing that. What could we write instead of this? Yeah, x squared. Let's do that. So if y is non-negative between 0 and 1, then sine of y is that, right? On the other hand, if minus 1 is less than or equal to y is less than or equal to 0, right? If y is negative, or I should say non-positive, between 0 and 1, minus 1 and 0, then the sine of y is equal to minus the square root of 1 minus x squared. Because sine of y is positive and negative depending on whether you're to the left or to the right of 0, right? Yeah.
With the 0 on both those cases, what would you do with that if you had?
Hmm. Oh no. Y equals 0. Well, sine of... Okay, so, I mean, sine of 0, they're both 0, right?
This wasn't sure if you had equal to on both.
Well, it's not wrong. I mean, I can erase one of them if you'd like, but
Well, it doesn't.
let's say this. Probably some of these mysteries will be cleared up if I just graph the inverse. Oh no. So this point flips over to that point, right? This point is fixed. And let's see, this point is what? Pi minus 1. So that flips to minus 1 pi. It's like up here. And let's see here. Oh, goodness gracious. This point was what? Pi over 2, 0. So that flips to 0 pi over 2, which is like up here. I can't draw worth anything. I mean, like I said, I'm like, it's stupid. I can never graph these worth anything. It's something, good grief, look at that. It's something like this. That is not quite right. I'm going to draw it in its own, I can't, yes, it's like that. It's running cosine up the y-axis rather than over the x-axis. It's the same shape, just run vertically. So when you think about y equals to 0, that's I'm trying to think of this. I'm all turned around and upside down. Okay, so both of these agree. When y equals to 0, they're both sine of 0, 0, right? So the cases glue together there. The thing that's bothering me is like, what's x in those cases? If this is 0, I guess x has to either be what? Plus or minus 1, right? So that's what's bothering me. X is plus or minus 1. I guess it's just that x equals plus 1 goes to the, well, of course, well. I'm sorry, I've lost track of what the question is. I got to stop. You asked a reasonable question. It's just I had an unreasonable response. Oh, man. Now you guys got me lost. Let's see here. Curses. Where were we? So what I'm trying to get at here is this is somewhat complicated by the fact that this is both positive and negative between minus 1 and 1. So I think someplace I need the positive square root, another place I need the negative square root. Like case-wise, right? So now I'm addressing the thing you were pointing out about the minus and the minus giving the plus. So if you think about this, so I should do what? I should do minus 1 over the square root of 1 minus x squared. If what? If y is what? Y is what? Yeah. And then I should do what? Yeah, that's what I was thinking. Maybe I'm getting all twisted over something that doesn't actually matter, though. Because this is even possible. No, I mean, that's not. No. I'm an idiot. So, look. I'm sorry, guys. We should start over. Look. Duh. So, sine of y is what? We've got cosine squared y plus sine squared y is equal to 1, right? So sine of y is equal to 1 minus cosine squared y, right? Sine squared y, rather. So that means that sine of y is equal to either plus or minus the square root of 1 minus cosine squared y, which is what? Right. Okay, so just focus on that. Now, this is, by the graph, less than 0, right? So what does that say? Yes, that's right. And this is a square root of a quantity, right? That is, by definition, a positive thing. Or it could be 0 if x is plus or minus 1, right? Certainly, the square root itself is not negative. So that means I have to put dy dx equals to minus 1 over the square root of 1 minus x squared. Game over, end of story, because that formula makes us have a negative quantity between minus 1 and 1 for x, right? So excuse my confusion. There's really no need for breaking into cases. Does that make sense? Yeah. And I think we probably could even use that same logic last lecture, right? You could just look at the square root thing in order to say, oh, well, wait a minute, that's a positive thing, ignoring the plus or minus. And I know the formula has to either be positive or negative, so I can just go on the basis of the final result. What is true is that sometimes this sign is the square root, and other times this sign is minus the square root. That's the tricky thing. Well, that can't be right, though, because it's always minus 1. I'm sorry. I have found a way to confuse myself about this. I am very sorry. All right. Where's my... Oh, sorry. I left my stuff back there. Let me show you how... Let me show you how... So how does a book define inverse secant and inverse cosecant and such? Actually, before I do that, I think I need to give you guys a brief review of what we know from trigonometry, right? So, in particular, I should talk to you about trig identities. What trig identities do we know? Well, I think you know we've already used cosine squared theta plus sine squared theta is equal to 1, right? What are other important trigonometric identities that we should just know? I guess we divided this by sine squared, right? We also have 1 plus tangent squared equals secant squared theta, right? And closely related, cotangent squared plus what? 1 cosecant squared theta. Okay, so those are your basic ones. The next level of sophistication, I suppose, probably is this. Cosine of theta plus beta is equal to cosine theta cosine beta minus sine theta sine beta. And this is the so-called adding angles formula for cosine, right? The adding angles formula for sine is sine theta plus beta is, let's see here, sine theta cosine beta plus sine beta cosine theta. I guess there's another sort of more basic thing we should know about sine and cosine, which is what? Cosine of minus theta is cosine theta, and sine of minus theta is minus sine theta, right? Cosine's even, sine is odd. So with that in mind, what happens if you put a minus in the adding angles formula for cosine? Right, so I get, yeah, that puts the plus over here, right? Because this gets cosine minus theta, cosine minus beta, still cosine theta, cosine beta. And then over here, you get, cosine theta, cosine minus beta is just cosine beta again. Here, sine of minus beta pulls out a minus, and that's why we have a plus. You guys ever seen this notation? So the way this works is the plus, oh, I'm sorry. This way. The point is, the top one goes with the top one. So like plus goes with minus, and minus goes with plus. It also happens to be color-coded at the moment, but color coding is not necessary. Now down here, you get plus minus plus minus. In other words, if we have a difference, it goes to a difference in that way. Now, let's see here. What else could we do? What about tangent? What about tangent of theta plus beta? You just divide these identities, right? So you got yourself, well, tangent theta before that is sine theta plus beta over cosine theta plus beta. I mean, the thing I haven't written yet, which is also important, is just the definitions of like tangent, cosecant, secant. I won't write those. Here's one. Tangent sine over cosine. But we know that this is what? This is sine theta cosine beta plus sine beta cosine theta divided by cosine theta cosine beta minus sine theta sine beta. Then what you can do is you just divide this whole thing by cosine theta cosine beta. So I'm dividing the top and the bottom by cosine theta cosine beta, which assumes what, by the way? I must be assuming something about beta and theta, right? That they're different. How about that cosine theta and cosine beta are both non-zero? If I'm dividing by cosines. So they better not be like plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, and so forth. Do these simplify? It does, in fact, yeah. What do we got here? These cosine betas cancel. Yeah. Yeah. Yeah, so we can rewrite this in terms of tangents of theta and beta. What do we got? We got tangent theta plus tangent beta divided by 1 minus tangent theta tangent beta. This is the adding angles formula for the tangent function. A little bit more complicated, but not out of reach. So that's kind of neat. Any questions? What other kinds of trigonometric identities are we going to need in here? How about like the half angle formulas or the double angle formulas, whatever, I forget which one's which. How do you get those? Here, I'll show you the conventional wisdom way to do it. Something like this. If I take theta plus theta, what do I have? And so go back over here, put beta and theta both be theta. What do you get? You get cosine theta, right? So you get cosine squared theta minus what? Minus sine squared theta. But what's that? No, not 0. That would be simpler. 1. Here, we're insistent on only looking at cosines. How about that? So how can I convert the cosine to a sine? Sine squared is what? It's 1. Right, I'm using the Pythagorean identity there. And minus minus gives me plus, right? So this gives me cosine 2 theta equals twice cosine squared theta minus 1. And now I can solve for cosine squared, right? I mean, I guess that's an identity. Cosine of 2 theta is this. I rarely find myself needing to use that identity. Almost always in this course, I need to use the following. Solve for cosine squared theta. Cosine squared theta is what? 1/2 of 1 plus cosine 2 theta. That's an important formula to know. That's one of those ones I have memorized. So what does that say about sine squared theta? You can see from this formula, right? If you subtract that from 1, what do you have? 1 minus 1/2 is what? 1/2, right? So you get 1/2 minus cosine 2 theta. So it's the same thing. And if you think about that for a second, you see that has to be the case. Why? Why does it, it has to be such that, these formulas have to be such that when you add them, you get back to 1, right? Because sine squared plus cosine squared is 1. So it must be plus cosine 2 theta and minus cosine 2 theta on the other. Once you know one's plus cosine 2 theta, the other one has to be minus cosine 2 theta. So there's your, I think I usually call these double angle formulas. I don't know what the standard name is for them, but it's good. Now let's see here. What else we could do? We could put theta. How about put, what's sine of theta plus theta? Well, it's sine theta cosine theta plus sine theta cosine theta, right? Yeah, so sine of 2 theta is equal to 2 times the sine of theta cosine of theta. We use that in physics to derive the range identity, for example. So these are the big ones. Now there's more than this, though. And one of the things I'll share with you, which is not in the book, is the technique of the imaginary exponential, right? Now is probably not a good time to do it. We don't have time to do that today, but someday I'll come back to this topic, and I'll show you how we can derive these identities through one simple means. See, the sort of undesirable thing about the way we did it right now is, suppose you're looking for an identity for cosine squared theta, right? Suppose you didn't know this. How would you find that? You have to go, it's rather indirect, the thinking, right? I have to think, well, I know this double angle formula, and I guess if I put theta and theta, then I'll get a cosine squared theta here, so that must show it to me, right? The other way I have of doing this, you can just directly take whatever it is you're trying to simplify, convert it to imaginary exponentials, do usual algebra, out pops identities. It's really neat. Okay, but I have a strong suspicion we're going to miss Friday, so I'll put that off till next week. All right, so moving along here. The way that the book defines arc sine and arc cosine, well, oh, I'm sorry, there's one other, well, my principal weakness is indecision, so you'll forgive me. Inverse sine of x plus cosine inverse of x is equal to pi over 2. In fact, this is what the book says is the definition of arc cosine. And I'll have to think about more. I have to think more about why this is the definition. I usually have just thought it's the local inverse for the restriction in my past thinking. So this definition the book gives, a little bit new to me. Secant inverse plus arc cosecant inverse is, you guessed it, pi over 2. Now, oh, this is not the, I'm sorry, he does not say that's the definition. I'm sorry, these are not these are not, this is, these, sorry, these are just properties. So this is on page, it's a boxed, it's 7.7.11 on page 384. Now, so the definition was a little bit different. It's like, how does he define inverse secant of x? How does he define that? It's a little bit above this box. He says the definition of inverse secant of x is that it's cosine, inverse cosine of 1 over x. All right. So, given that definition, you can show that. Well. Oh, and also, what's the definition of inverse cosecant? I think once you have this, you can see what the definition of inverse cosecant is going to be. Right. Right. All right, so he proves that inverse cosine plus inverse sine is equal to pi over 2, all right? And then he leaves the second two things in these properties as homework problems. I'm a little nervous. Do you want me to try one? Like, wait a minute. Have I assigned you one of those? 73 and 74. In section 7.7? No. It occurs to me I should take attendance, right? There may be somebody here who was not here yesterday. I should count them as attending, you know. Let's see here. Here, I'll start with you and then pass it back and zigzag. Okay. If you've already signed, you can just pass it on. I just need one signature, really. Yeah. This is so I can mark you have attended in Blackboard. So if you've already signed it, you're good. Okay. But if you haven't, Yeah. As usual, I should tell you, don't sign it if you're not here. All right, so well, let's see here. How would you prove one of these? So I'm gonna set aside that problem actually because I got stuck on that thing earlier and now I'm behind. I'm sorry. Anyway, these are the definitions, so we can figure out what is the derivative of inverse secant just from this in the chain rule, right? What's the purpose of this property? What does this tell us? I mean, if you already have these identities, you don't need to do some of the work I was already doing earlier, right? Like, what does this first one tell you? This tells us that the derivative with respect to x, if I differentiate this identity, I have that the derivative of inverse sine, the derivative of inverse sine x is going to be equal to minus the derivative of, inverse cosine x, right? And this one would tell me that the derivative with respect to x of, well, more interestingly, let me just say cotangent inverse of x is equal to minus d dx of tangent inverse of x. And since we already calculated this one, we already know that this is minus 1 over 1 plus x squared, right? Now, the gap in my argument is what? Is that I haven't proved this property. That's homework problem 73 and 74. I'm going to look at that on my own time. If I can figure it out, I'll post a solution for you guys to look at. I don't want to burn class time. The proof of inverse sine plus inverse cosine being pi over 2 is in the book. That might be worth looking through. I'll come back to it if we have time. I think I should move on. Okay. So, I will focus now. Here's our definition of inverse secant, our definition of inverse cosecant. So what's the derivative of inverse secant? How do we figure that out? So the definition says it's the derivative with respect to x of inverse cosine of 1 over x, right? And now we know that that's minus 1 over the square root of 1 minus 1 over x quantity squared times d dx of 1 over x. What did I just use there? I used the thing I botched the derivation of earlier today, the inverse cosine. Oh, it's gone. That's all right, I erased my sins. And then the chain rule, of course. So what do we got? Minus 1 over the square root, 1 minus 1 over x squared, times what? Minus 1 over x squared, right? Can we, I guess we can simplify that a little bit, right? So this is 1 over x squared times the square root of 1 minus 1 over x squared. See, can we clean that up at all? What's he do here?
d over dx, 1 over x. Oh, I don't see that.
Chain rule. The chain rule. Oh, sorry, I'm kind of mystified by some of his simplification at this point, but it's not a big deal. Okay, so what can you do now? I wonder if you guys know this. Let's see here. So x squared is equal to the absolute value of x squared, right? Right? Is this true? How could you define the absolute value of x, by the way? A nice formula for it is just the square root of x squared, right? So of course, if that's true, then this is true. I mean, I take this to be the definition of absolute value. So anyway, what does that allow us to do? If we have d dx of the inverse secant of x, we have 1 over the actually absolute. So I can trade my x squared for what? Absolute value of x, quantity squared. So what you can do then is you can peel off one of those and bring it inside, right? So I've got the absolute value of x, quantity squared. See what I did there? So if I have a times the square root of stuff, and if this a is positive, right, then this is, well, the square root of a squared, right, times the stuff. I guess more generally, if I erase this condition that a is positive, I can pull in, well, I got to be careful. If a is negative, I got to put a minus outside and stuff, but definitely absolute value of x is positive, so I can pull it in and make it absolute value of x squared, right? And then what happens? Remember, absolute value of x squared is just what? X squared. So then I have x squared times this, which just leaves me with x squared minus 1. And there you go. There's your takeaway formula that the book has. d dx of inverse secant of x is this. All right.
Can you explain how you went from where you have the absolute value of x squared and then this stuff that you brought like one on the side and one on the side? Like how's there an x squared inside and then one is outside?
Because this is this. So what I'm doing. So what I'm doing is I'm bringing this copy inside, and when I do that, I have to square it, because that's the way, you know. Yeah. The book has a slightly different argument. All right. I'm sorry. I think I'm getting lost in the weeds in this section. I really should probably have moved on a while ago at this point. I'm sorry about that. So this brings us to our next topic. I mean, there is more to say here. So the next section is on what are called hyperbolic functions. So I'm sorry, there's definitely something missing from my presentation in the last section. I'm sorry about that. If you read the section, I think it'll make sense to you. We've done a lot of it, we just haven't done quite all of it, and sorry about that. So hyperbolic functions, what are hyperbolic functions? Okay, so hyperbolic trigonometric functions, you know, so hyperbolic trig is maybe a better title here. What is that about? So do you guys know that any function that's defined on a symmetric interval about the origin can be broken into a sum of even and odd functions? Have you ever heard this? Let me show you something that's true. So if I have f of x, right, I can rewrite this as 1/2 f of x plus f of minus x plus 1/2 f of x minus f of minus x. It's not too hard to convince yourself that this is an even function and this is an odd function. I just need what? X and minus x are in the domain of f. So the domain of f has to be such that it's like symmetric about the origin. If that's the case, you can rewrite the function as a sum of an even function and an odd function by this simple identity. See what I did? I added 0. Did you see it? if you apply this simple identity to the exponential function, e to the x, right, what you get is 1/2 e to the x plus e to the minus x plus 1/2 e to the x minus e to the minus x. All right? This identity is part of what motivates the definition of this. This is the so-called hyperbolic cosine of x. And this over here is the hyperbolic sine of x. So cosh and sinh, as they're called, are respectively the even part of the exponential and the odd part of the exponential. So do you see what I'm saying the definition is? Yeah? What happens, so these are fun. What happens if we multiply cosh x times sinh x? What do we get? We get a fourth, right? What's e to the x times e to the x? Yeah, e to the 2x. And then I get what? Plus 1, minus 1, because e to the x times e to the minus x is e to the 0, which is 1. And e to the x times e to the minus x is minus 1, because we get plus, plus, minus, minus, plus. And then I get minus e to the minus 2x. Hey, what's that? That's 1/2 of 1/2 e to the 2x minus e to the minus 2x. Which is what? It's 1/2 of the hyperbolic sine of 2x. Well, that's weird. Hey, wait a minute. Didn't we just do that? So I just found sinh of 2x is twice cosh x minus sinh x. That's an, oh, did I say minus? Good grief. Guys, don't let me get away with that. Right? Duh. See, they start to understand why they're called hyperbolic trig functions. They behave much the same way as the regular trig functions. Okay? What do you think we'd get if we looked at like cosh squared plus sinh squared? Well, it's not 1. What is 1 though, if you change that plus to a minus, you'll get an identity, right? So this is the other fundamental identity. Cosh squared x minus sinh squared x is equal to 1. This is true. We can prove that. Tell you what, I'm going to prove it in a somewhat sneaky way, if you don't mind. So let's see here. How about this? Cosh squared x minus sinh squared x is equal to what? It's cosh x minus sinh x times what? How do I know that? What did I just do? I just did, we call this in algebra the difference of perfect squares, right? A squared minus b squared, a plus b times a minus b, vice versa. When did we start? Am I done? When's class end?
I don't know.
I'm gonna finish this, then I'll shut up. Man, I tell you guys. You know, I was here early and I prepared for class. Isn't that the irony of it? It's the worst. If I don't prepare for class, lecture goes better. Isn't that weird? It's true though. So cosh, you notice cosh and sinh are even. I mean, excuse me, what is, sinh is odd, right? So if you look at this, this is actually cosh of minus x plus sinh of minus x, right? So this is exactly e to the minus x, and this, of course, is e to the x. If you go back to how we motivated the definition of cosh and sinh, right? You have this identity, e to the x is cosh x plus sinh x, right? So using that over here, cosh x plus sinh x is e to the x. Cosh minus x times sinh minus x is e to the minus x. But what's e to the x times e to the minus x? E to the 0, right? Which is, and there you have it. That's one way to prove the sort of Pythagorean identity for hyperbolic trig functions. Anyway, I have much more to say about hyperbolic trig functions tomorrow, and that's what we'll get back into. Sorry about the events of today.